So we are going to talk about one of the properties of the wave functions in the infinite square wave. As we have solved for the wave functions, there are certain properties that you have to know for the respective wave functions. So what we're going to talk about is that, first of all, we have derived in our previous video. You can watch the video in the quantum mechanics playlist, that the wave function for the infinite square wave is something like that. More it is like an eigenfunction. Okay, so this particular eigenfunction is a root under 2 by a, and it is a sine function, and there is a reason why there is a sine function. You can watch that they behave like some sort of standing waves, and their forms and nodes and all that stuff I have mentioned in my earlier videos of the infinite square wave. So this is a property that I'm going to, which is the orthogonal wave functions. Okay, so it is like we depicted our wave functions, we like n pi x and divided by a. So this is what the representations of our wave function for the infinite square wave. Here n is the label for the wave functions for the different energy level. N is equals to 1, n is equals to 2, and all that stuff. Okay, so the property is that, suppose that you have a wave function, let's say psi of n, and a wave function psi of m, and it is a condition that m is not equals to the n. So the property of this particular orthogonal wave function is that the integral of psi of m complex conjugate and then multiply with the psi of n, and when then we took the integral of this is equals to the 0 if m is not equals to the n. So this is the very important property that you have to know, and I'm going to prove this. I have stated this particular in my previous videos, but I haven't done the proof of this, so I'm going to do this now, and we are going to do this here. So what will happen if m is equals to n? So we'll talk about it later, that what will happen if m is equals to the n. So let's start the proof. So let's start it, and there's some sort of properties of the trigonometric functions that are going to use here, so be prepared for that. So the integral of sine of 1 minute, there is a factor of root 2 by a. I don't want any confusions that you might have. I will not skip any part of the calculation. Okay, so root under 2 by a sine of m into 1 minute. Yes, sine into mx by a into pi, and then again root under 2 by a sine into pi x n by a dx. So this is our particular integral. Let me write it here. This is our a very beautiful integral of psi of, and from 0 to a, of course. Okay, from 0 to a of psi of m psi of n, here is complex conjugate, dot dx. So this is our integral. So let's evaluate this now. I can just multiply this root under 2 by a to get 2 by a, and just remove it from this particular integral as it's constant, and we have sine of here mx pi divided by a multiplied by sine of n pi x divided by a dx. So now here I'm going to use a property for the trigonometric identity, that sine a into sine b. Okay, and it's a well-known property that sine a into sine b is equals to cos m minus x. It is also a factor which is of 1 by 2 as a whole. I am depicting this. Okay, so m minus n, 1 minute, m minus n, and here should be also pi x. Okay, and divided by a. So this is our first thing, it's all in the bracket. Then of course minus, we have cos of n, okay 1 minute. Okay, so cos of n plus m, and here of course in the bracket there is pi x and divided by a as a whole, and of course there is dx. Okay, so this is our particular integral. Now evaluating this further, we can do this as 2 and 2 will cut out from integral 0 to a. So this is our integral, and this is a pretty easy integral. Yes, this is easy. So 1 by a, the integral of this, let me write it clearly from 0 to a so that you will not be confused. So this is like cos of m minus n by a pi x minus cos of n plus m by a pi x. Remember, pi x is for those m and m, for both of that, not only for a single n or m. Okay, so this is our integral, and this is quite easy integral. You can use the method of the substitution for this particular thing. You can assume, let me write it, that this particular integral is easy. You can assume as a sine of m minus m by a pi x as t, and then differentiate this particular function, and after differentiating it you will get this, and additional here with this particular term with x removing, and you can use, this is a very easy integral. I'm not doing this. Yes, I have said previously that I will try to not to avoid any step, but this step is very easy. Anyone can do this particular from the method of substitution. Okay, so this is integral 0 to a, and if you evaluate this integral, you will get 1 by m minus n pi, and a here in this, but a and a will eventually cut out, but I'm writing this. Okay, and here of course here will be, after integral, sine of m minus m by a minus, okay, pi x. For this particular part, it is 1 divided by m plus n pi, and here of course sine of n plus m by a, let me evaluate it, pi x. Oh, 1 minute, I have to remove this sign of integral because I have done that. Okay, so here it will be 1 by a, let it put in this particular sign, and also I have to write here a, because if I have done the integral I have to put the limits here, and after limit here it should be pi a, which will eventually cut out, but you have to write it. So this is a pi a, and here also here should be pi a. Oh, okay, now it's good. So, and here it should be also a. Now it's good. Now you can take a common here, so this will eventually cut out from this, and let me evaluate it now. So this is equals to the 1 by m minus m pi sine m minus n, a and a will cut out, pi as a whole, pi as a whole. Okay, this is the condition, and minus 1 by m plus n pi sine of n plus m, a and a will cut out, and here it's pi. Pi is as a whole. Again, I am telling this, pi is as a whole, not on a single. So to avoid this, I will put it in a bracket so that you will not be confused though. Okay, so this is the condition for our integral, and we have evaluated this particular integral. Now here's a very important observation that you have to see, and it's very important. It's like, if m is not equals to n, what is happening there? So to prove this, you can generally say that suppose that I have taken my m as a 2 and n as 1. You have chosen this. Okay, now you can just evaluate this. What do you mean by evaluation? I mean just put it down 2 and 1 in this respective equation and see what will happen. So if I will put m as 2 and n 1, let's see what will happen. It will be like sine of m minus m, which is 1, and this is sine, it will be sine pi. Okay, and minus, if you will plug on there, it will be sine 3 pi divided by 3. Here should be also pi and pi. Okay, and you know that sine 3 pi is 0 and sine pi is also 0. So no matter what you will put, if they're consecutive, this is also a thing that if they are consecutive, then you can always do that. Let me put some another number to clarify that you have to do, let's say 2, and let me think of, okay, let's say now ms3, okay, and ns1. Even though you will put this down, what you will see is that you will put 3 plus 1 4, eventually you will get sine 4 pi, which is 0. Sine pi is 0, and any multiple of pi like 1 pi, 2 pi, 3 pi, 4 pi, all is 0. So what does that mean? So it means that no matter what you will put, if m is not equals to n, then you are getting this particular integral as 0. Otherwise, what will happen? Okay, so this is now a good question. So let me put it here, that the this which color, okay, so let me choose. So integral of psi of complex conjugate of m dot psi of n dx is equals to canonical delta mn. What is the meaning of this? Meaning of this is that canonical delta will give two values. One, if m is equals to 1, then if m is equals to n, it will give 1, and if m is not equals to n, as I have taken the example now, then it will become 0. That's why we have here choosing the canonical delta, not only 1 and 2. So canonical delta is a kind of representation of this, that if m is equals to n, and if not, how? Also see here, if m is equals to n, what it will be? It will be simply the psi mod square dx, which is normalization condition, and it is equals to 1, of course. That's why when m is equals to n, there is a mod of psi square dx, which is none other than the normalization, and the value of normalization is always 1, and that's why when m is equals to n, the value of this particular integral, it means this integral is 1. Pretty easy. Yeah, it is pretty easy. Okay, so this is the condition. Let me write it now clearly, that the orthonormal condition of a psi of mod of m into psi of n dx is equals to the canonical delta. So this is my today's video, on which I have discussed about this particular canonical delta stuff and the orthonormality condition. So it is a very important property and also a very powerful property. So that's for today.